In this video, we will be discussing certain types of problems involving everything that we learned so far. And I suggest watching the previous videos before continuing with this one. You can pause the video after every question to try it yourself first before watching the solution. The first question is, in how many ways can we place the letters of the word action in the 8 boxes of the given figure, such that no row remains empty? There are 6 distinct letters in the word action, and we need to put them in the given 8 boxes in all possible ways such that no row remains empty. The first thing to do is to form examples. Not doing it is possibly the main reason why many find permutation problems hard to solve. Forming examples involve doing whatever is being asked in the question. In this case, we are asked to place 6 given letters in 8 given boxes. So let us place them. Note that we are forming examples without worrying about any condition, placing letters wherever and however we want. Since we are arranging 6 distinct letters at 8 places without any restrictions, so total number of arrangements is 8p6. Let us go to the examples again. Since there are 6 letters and 8 places, so we always have 2 blank places in every arrangement. These 2 blanks can be anywhere except when they both are at the top row, because then this first row will be empty, or when both the blanks are at the bottom row, causing this third row to be empty. Apart from these 2 cases, none of the other arrangements will have any row empty. If we are leaving the top row empty, then 6 letters in the 6 remaining boxes can be arranged in 6 factorial ways. Similarly, if we are leaving bottom row empty, then 6 letters in the remaining 6 boxes can be arranged in 6 factorial ways. These are the only number of arrangements in which some row is left empty. So excluding them from the total, we get the number of required arrangements. Next problem is to find the total number of divisors of 2520. We want to find those numbers which can perfectly divide 2520, leaving no remainder. Let us take a number, say 16, and divide the given number 2520 by it. Since the division leaves some remainder, so 16 is not a factor of 2520. Let us take another number, say 18, and divide 2520 by it. This time the remainder is 0, that is 18 perfectly divides 2520 and so is one of the divisors that we want. To understand why 16 isn't and 18 is a factor of 2520, or why does 18 perfectly divides 2520 leaving no remainder, we need to recall the concept of prime and composite numbers. A prime number has only 2 divisors, 1 and itself, whereas a composite number has more than 2 divisors apart from 1 and itself. Every composite number can be expressed as the product of primes. In other words, a composite number can be further broken down in prime pieces. Going back to our question to see what makes a number divisor of another number, let us break down 2520 as product of primes. So we have 2520 as 2 cube, 3 square, 5 and 7. Also 16 is 2 to the power 4 and 18 is 2 times 3 square. Now if we divide 2520 by 16, then we can see that the quotient is not an integer, so 16 is not a factor. But when divided by 18, it cancels out perfectly and the quotient is an integer. What about this number, 210? Is it a factor of 2520? Since 210, when expressed as product of primes, is 2 times 3 times 5 times 7. So when we divide 2520 by 210, the denominator cancels out completely, resulting in an integral quotient, making 210 one of the divisors. So we can see that for a number to be a divisor of 2520, it must be a subset of this set containing prime factors of 2520, so that we get an integral quotient on division. Some subsets or divisors are as follows. Observe that each of these divisors are formed from same prime factors that the dividend has, and also that the power of these prime factors do not exceed the number that they have in the dividend. So we can say that any factor of 2520 is of the form 2 to the power a, 3 to the power b, 5 to the power c, 7 to the power d, where a ranges from 0 to 3, as the power of 2 in the divisor cannot exceed the power of 2 in the dividend. Similarly, b can be any value from 0 to 2. C and D can either be 0 or 1 because in the divisor 5 or 7 can appear either once or none at all. So to form factors of this form, we can select a power of 2 in 4 ways, power of 3 in 3 ways, power of 5 in 2 ways, power of 7 in 2 ways. By product rule of counting principle, total number of divisors is 48. Next problem is to form 5 distinct digit numbers from the given digits such that they are divisible by 2, 3, 4 and 6. So we need to form 5 distinct digit numbers using the given digits from 0 to 5. Note that we must fill those blanks first which have some condition imposed on them. Since the number has to be divisible by 2, so the units place must be some even digit. Also, since the number has to be of 5 digits, so we cannot have digit 0 at the first place. Rest of the blanks have no condition and we can place any digit on them as long as we don't repeat digits. Since there are 3 even digits, so the units place can be filled in 3 ways, by 0, 2 or 4. Now of these 3 choices, if we select digit 2 for the units place, then we cannot use it again, and then for the first blank, we have 4 choices. But if we select 0 for the units place, then excluding it, we have 5 choices for the first blank. So we have this ambiguity in choices for the first blank according as 0 is or isn't in the units place. In such cases, we deal them separately by classifying them as numbers ending with 0 or numbers not ending with 0. In the first type, since the numbers have to end with 0, so units place can be filled in just one way, that is by 0. Since we have already used 0 for the units place, so we don't have to worry about the first blank, and we can freely permute remaining 5 digits at 4 places in 5p4 ways. So number of numbers ending with 0 is 120. Now for the second type, the number shouldn't end with 0, and also the units place must have some even digit, which leaves us with 2 choices. Let us strike out any one of the digits 2 or 4 as we cannot repeat digits. Now the first blank can be filled in 4 ways excluding 0. Let us strike out one more digit as we have used it for the first blank. Now the remaining 4 digits on 3 places can be permuted in 4p3 ways. So the number of numbers not ending with 0 is 192. By addition rule of counting principle, the number of numbers divisible by 2 is 120 plus 192, 312. In the next bit, we need to form numbers that are divisible by 3. Note that a number is divisible by 3 if the sum of its digits is divisible by 3. For example, this number, 4815, has the sum of digits as 18, which is a multiple of 3. So the number itself will be divisible by 3. In fact, number formed from these same digits will all be divisible by 3. We need to form 5-digit numbers, but we have total 6 digits. The total sum of all these 6 digits is 15, which is a multiple of 3. If we exclude 0 and select digits from 1 to 5, then the sum of digits will still be 15, and so numbers formed from these selected digits will all be divisible by 3. These 5 digits can be permuted in 5 factorial ways. So we have 120 numbers formed from the digits 1 to 5 that are divisible by 3. Since 15 is the total sum of all digits, so we cannot have a sum greater than that, and thus we go lower to 12, which is the next multiple of 3. To have 12 as the sum of the digits, we exclude the digit 3 and select other 5 digits 0, 1, 2, 4, 5. These 5 digits, including 0, can be arranged in 5 factorial ways. But of these 5 factorial arrangements, those that start with 0 are 4 factorial. And we must exclude them as 0 in the first place makes them a 4-digit number instead of a 5-digit number. So we have formed numbers from those digits which add up to 15, digits that add up to 12, and now we cannot go any lower than this sum of 12 because for the numbers to be divisible by 3, we would now need the sum of digits to be 9. And even after excluding the greatest digit 5, we still are getting the sum minimum as 10, that is greater than 9. So there is no other possibility, and required numbers that are divisible by 3 can be formed in either of these two ways. By addition rule, total number of ways is 216. In the next bit, we need to form numbers that are divisible by 4. Note that a number is divisible by 4 if the number formed by the last two digits is divisible by 4. Suppose we have this number 21,628. Then to know if it is divisible by 4, we look at the number formed from the last two digits, that is 28, which is a multiple of 4. So this entire number is divisible by 4. We want to form 5 distinct digit numbers from the digits 0 to 5. Their divisibility by 4 depends on the digits that we place on the last two blanks. We can place 24 or 52 or 40 and so on. We want to find all such possible last two digits, and haphazardly guessing them is not a good approach. Instead, we can systematically start with 0 and pair it with other digits like 01, 02, 3, 4, 5. Of these, only 04 is a multiple of 4, and so can be the last two digits. Next, starting with 1 and pairing with other digits in the same way, we have 12 for the last two digits. Proceeding similarly, we get the digits that we want to place in the last two blanks. So the numbers divisible by 4 can be classified in the following types. If we fix 0 and 4 at the last two places, then we are left with 4 digits and 3 blanks to fill, which can be done in 4p3 ways. If we fix 1 and 2 at the last two places, then we are left with 4 digits including 0, which cannot be at the first blank. So the first blank can be filled in 3 ways using any one of the non-zero digits. Remaining 2 blanks can be filled in 3p2 ways. So numbers ending with 12 are 18. Using same arguments, we get the following results. Since the types in our classification are all exclusive, so the required answer is the sum of all results. For the last bit, numbers have to be divisible by 6, which means they have to be divisible by both 2 as well as 3. Now we have already discussed them individually in bit A and B. For the number to be divisible by 2, the units place must have some even digit, and for divisibility by 3, the sum of the digits must be a multiple of 3. Both these conditions must be satisfied simultaneously. Try this yourself, and the answer is 108. See if you are getting the same answer. The next question is to form 4-digit numbers from the given digits and then to find the sum of all those numbers. Before we start with this question, let us discuss some things first. Suppose we have this number 4342. It has 4 digits and their place values are ones, tens, hundreds and thousands. Had the number been of more digits, the place values would have increased by powers of 10. Digits of a number add value according as where they are placed. For example, this digit 4 adds a value of 40 to the number, whereas this digit 4 adds a value of 4000. So we have this number as 4 thousands, 3 hundreds, 4 tens and 2 ones. Suppose we have a list of numbers. Sum of the digits in the units column is 14, tens column is 20, hundreds column 7, thousands column 1 and 10,000s column 2. So this list of numbers has 14 ones, 20 tens, 7 hundreds, 1 thousands and 2 10,000s, which adds up to 21,914, which obviously is equal to the sum of this list of numbers. Another thing that I would like to discuss is, in an arrangement, the occurrence of a particular term at a specific place. Suppose we have 4 distinct objects, then these can be arranged in 4 factorial, that is 24 ways, if repetitions are not allowed. Let us list all of those ways. Now, how many of these arrangements have object A at the first place? To know this, let us fix A at the first blank. Then the remaining 3 objects can permute in 3 factorial, that is 6 ways. So there are 6 arrangements in which A is in the first place. Let us verify this. In the first place, we can see that A appears for 6 times. Just like A, if we fix B at the first blank, we will have 6 arrangements that start with B. So B also appears for 6 times in the first place. Same goes for C and D. They too appear for 6 times each in the first place. We can show this same result by fixing objects at any of the 4 blanks. So if we take any column, we can see that every object appears for 6 times each. So the composition of objects in each of these columns is same. That is, each column has 6 A's, 6 B's, 6 C's and 6 D's. Only the order of placement is different. Going back to our question, we need to form 4-digit numbers using the digits 1, 3, 5 and 7 and then find the sum of all those numbers. If repetitions are not allowed, then the number of numbers that we can form is 4 factorial, that is 24. In this list of 24 numbers, number of times that 1 appears at the units place is 3 factorial. Similarly, 3, 5 and 7 each appear for 6 times in the units place. So the sum of the digits in the units column is 96. As we have already discussed that every column has same composition, that is, in every column, the digits 1, 3, 5 and 7 appear for 6 times each. So the sum of every column must be 96. Now since we know the sum of every column, so the total sum of this list of numbers has value of 96 ones, 96 tens, 96 hundreds and 96 thousands. which adds up to 106656. So this is the sum of all 4 distinct digit numbers that can be formed from 1, 3, 5 and 7. In the next bit, the numbers that we form can have repeated digits. So now if we fix a digit, say 1 at the units place, then the remaining blanks can be filled in 4 ways each. So the number of numbers that have 1 at the units place is 64. Same applies for other digits 3, 5 and 7. They all appear for 64 times in the units place. So sum of digits in units column is 1024. In fact, the sum of digits in all 4 columns is 1024. So the sum of all the numbers that we can form is 1137664. That is all for this video. These are some questions that I would like you to try. Pause the video and take the screenshot. In the next video, we will be discussing permutation of things that are not all distinct. Until then, go through the given questions. You can also start solving from any book that you have. Feel free to make any suggestion or to ask any doubt. You can either comment below or mail me at this address.